The microscope is an optical instrument used to view objects of very small sizes. The apparent size of the object viewed through the microscope is many times larger than its actual size. Primarily, the apparent size of an object is determined by the size of its image on the retina, which in turn depends on the angle subtended by the object at the eye. When the object is far from the eye, it subtends a small angle at the eye, and hence its apparent size is also small. As it is moved closer to the eye, the angle subtended by it at the eye increases, resulting in the increase of its apparent size. We know that the closest distance for comfortable view is the least distance of distinct vision, or the near point, usually represented by D. When the object is placed at the near point, the angle subtended by it at the eye and its apparent size is the greatest. If the object is closer to the eye than the near point, the eye cannot focus its sharp image on the retina. But a simple microscope or magnifier can be used to view such objects without any strain on the eye. A simple microscope is a converging lens of a small focal length. If it is placed between the eye and the object such that the object distance u is less than its focal length, then the erected magnified virtual image of the object is formed beyond the near point. The angular magnification, or the magnifying power of a simple microscope, is the ratio of the angle subtended by the image at the eye when seen through the microscope to the angle subtended by the object at the unaided eye when it is placed at the near point. If theta is the angle subtended by the image at the eye when the object is seen through the simple microscope, and theta naught is the angle subtended by the object at the eye when placed at the near point, then the angular magnification, or the magnifying power m, is equal to theta by theta naught. Now, let us find some useful expressions for the magnification of a simple microscope. If the height of the object is h, then tan theta naught is equal to h by d. But for small angles, tan theta naught is approximately equal to theta naught. Hence, we can write that theta naught is equal to h by d. Let this be equation 1. When the object is viewed through a simple microscope, the angle subtended by the image is the maximum when it is formed at the near point, and minimum when it is formed at infinity. When a simple microscope is adjusted in such a way that the object is at a distance slightly less than the focal length of the lens, then the virtual image is formed almost at infinity. This situation is known as normal adjustment. When the simple microscope is set for normal adjustment, and the angle subtended by the image at the eye is theta 1, then tan theta 1 is equal to h by f, or theta 1 is equal to h by f. Let this be equation 2. If the angular magnification of the simple microscope when the image is formed at infinity is mi, then mi is equal to theta 1 by theta naught. On substituting the values of theta naught and theta 1 from equations 1 and 2. And on further simplification, we get the angular magnification or the magnifying power of the simple microscope as mi is equal to d by f. Let this be equation 3. Now let us find the angular magnification of the simple microscope when the image is formed at the near point. Let the angle subtended at the eye by the image when formed at the near point be theta 2. From the ray diagram, we can write that theta 2 is equal to h by u0. Let this be equation 4. If mn is the angular magnification of the simple microscope when the image is formed at the near point, then mn is equal to theta 2 by theta naught. On substituting the values of theta 2 and theta naught from equations 4 and 1, and on further simplification, we get mn is equal to d by u0. Let this be equation 5. But from the lens formula, we have 1 by u is equal to 1 by v minus 1 by f. Using the Cartesian sign convention, we can write that u is equal to minus u0, v is equal to minus d. Substituting these values in the lens formula and then multiplying both sides with minus d. And on further simplification, we get d by u0 is equal to 1 plus d by f. On comparing this with equation 5, we get mn is equal to 1 plus d by f. Let this be equation 6. From equations 3 and 6, we observe that the magnifying power of the simple microscope is greater when the image is formed at the near point than when it is formed at far point. We prefer to have the final image formed at the far point because the images formed at the far point can be seen by a relaxed eye with minimum strain. When greater magnification is required to view microscopically smaller objects, a compound microscope is used. A compound microscope consists of two convex lenses arranged coaxially. The lens O that is close to the object to be viewed is called the objective, and the lens E that is close to the eye is called the eyepiece. The objective of a compound microscope is of a small focal length and has a small aperture, whereas the aperture of its eyepiece is large. Let a small object AB be placed at a distance that is just greater than the focal length of the objective FO. When the light rays from the object are incident on the objective forms an image A'(B'), which is real, inverted, and magnified. This image A'(B') acts as the object for the eyepiece. If the position of the eyepiece E is so adjusted that A'(B') lies between the optical center and the first principal focus, then a virtual and magnified final image A'(B') is formed. Let the height of the object AB be h and the height of the image A'(B') formed by the objective be h'. Let us also define the tube length L of a compound microscope as the distance between the second focal point of the objective and the first focal point of the eyepiece. If MO is the magnification due to the objective and theta is the angle that the ray refracted by the objective makes with the principal axis, then MO is equal to H dash by H and tan theta is equal to H by FO, which is also equal to H dash by L. From these two equations, we get MO is equal to L by FO. Let this be equation 7. If the eyepiece is adjusted in such a way that the image A dash B dash is formed between the first focus FE and the optic center of the eyepiece, and it is very close to FE, then the final image is formed at far point. Then we say that the compound microscope is set in normal adjustment. Since the eyepiece acts as a simple microscope, using equation 3, we can write the magnification due to eyepiece ME is equal to D by FE. Let this be equation 8. Since the image formed by the first lens becomes the object for the second lens, the total magnification of the combination M is the product of the magnification due to the objective and the magnification due to the eyepiece. Therefore, M is equal to MO into ME. Substituting the values of MO and ME from equations 7 and 8, we get M is equal to L by FO into D by FE. That means, when set for normal adjustment, the magnifying power of a compound microscope M is equal to L by FO into D by FE. If the eyepiece is adjusted such that the final image is formed at the near point, then, using equation 6, ME is equal to 1 plus D by FE. In such a case, the magnifying power of the compound microscope M is equal to L by FO into 1 plus D by FE. For larger magnification, the objective and the eyepiece of a compound microscope must have small focal lengths. The magnifying power is generally expressed in terms of x, where x is the number of times the size of the image appears to be when compared to the size of the object. For example, if a compound microscope is marked as 10x, then its magnification is 10, and it denotes the number of times the size of the image appears to be when compared to the size of the object. In fact, the objective and the eyepiece of a compound microscope are made of a multiple lens system. This improves the quality of the image and minimizes various optical defects. The telescope is an optical instrument that is used to view distant objects clearly. The astronomical telescope is used to view celestial bodies, and the terrestrial telescope is used to view distant objects on the Earth's surface. Let us now study about an astronomical telescope. Consisting of two converging lenses placed coaxially. One of the converging lenses is called the objective, which is closer to the object to be viewed, and the other is closer to the eye and is called the eyepiece. To capture the image of a distant object, the objective must gather large amounts of light, and hence the aperture and the focal length FO of the object is large. The eyepiece of a telescope has a small aperture and a small focal length FE. When the telescope is turned towards a celestial object, parallel rays from the distant object are incident on the objective, which form an image AB at the focus FO of the objective, and this image is real, inverted, and of point size. The image AB acts as an object for the eyepiece, and the final image A-B- of the distant object is formed by the eyepiece. The image A-B- is virtual, magnified, and is inverted with respect to the original object. Let the angle subtended by the object at the objective be alpha. Since the object is far away, the angle subtended by it at the objective is same as the angle subtended by it at the eye. Let beta be the angle subtended by the final image at the eye. The angular magnification, or the magnifying power of a telescope M, is the ratio of the angle subtended by the final image at the eye to the angle subtended by the object at the unaided eye. That means M is equal to beta by alpha. Let this be equation 1. Let us now derive an expression for the magnification of an astronomical telescope when it is set for normal adjustment. The telescope is said to be set for normal adjustment if the final image is formed at infinity. If the image AB is on the focal plane of the eyepiece, then the final image is formed at infinity. Since the two angles alpha and beta are very small, tan alpha is approximately equal to alpha, and tan beta is approximately equal to beta. But tan alpha is equal to AB by FO, and tan beta is equal to AB by FE. Hence, for small angles of alpha and beta, we can write that alpha is equal to AB by FO and beta is equal to AB by FE. Substituting the values of alpha and beta in equation 1 and on further simplification, we get M is equal to FO by FE. Let this be equation 2. Hence, we observe that the angular magnification or magnifying power of a telescope that is set for normal adjustment is the ratio of the focal length of the objective to the focal length of the eyepiece. In this case, the length of the telescope tube is equal to FO plus FE. It is important to note that the final image formed by an astronomical telescope is inverted. There is no difficulty for the viewer as most of the celestial objects are spherical in shape. If the astronomical telescope is used to view a terrestrial object, then the final image being inverted would be a cause of discomfort for the viewer. To overcome this problem, we use a terrestrial telescope which produces a final image that is erect with respect to the object. placing a third lens, known as the inverting lens, between the objective and the eyepiece, we can get an erect final image. If the focal length of the inverting lens is f, then it is placed at a distance of 2f from the focal plane of the objective. When the telescope is turned towards a distant object on the ground, the rays from the object are incident on the objective, which form an image PQ on the focal plane of the objective. PQ is real, inverted, and diminished compared to the object. PQ now acts as an object to the inverting lens, and since this image PQ is at a distance 2f from it, the inverting lens forms an image P', which is real, inverted, and of same size as PQ. It is of importance to note that the image P', is erect with respect to the original object. The size of P', is same as that of PQ. The lens has merely made an inverted image erect. The image P', acts as an object to the eyepiece. If the object distance with respect to the eyepiece is less than its focal length, then a virtual image P', Q', is formed. The final image is erect and magnified since it creates a larger visual angle at the eye. We can adjust the position of the eyepiece such that P', Q' is formed on the focal plane of the eyepiece. Then, the final image will be formed at infinity, and the telescope is said to be set for normal adjustment. The magnifying power of the terrestrial telescope, when set for normal adjustment, is also equal to the ratio of the focal length of the objective to the focal length of the eyepiece. In some of the terrestrial telescopes, a pair of inverting lenses is used to make the final image erect. The main considerations of a telescope are its light gathering power and its resolving power. Light gathering power of a telescope depends on the size of the objective. If the size of the objective is large, then it can collect more light, and as a result, fainter objects can also be observed. The resolving power of a telescope is its ability to observe two objects in very nearly the same direction distinctly. The resolving power of a telescope also depends on the diameter of the objective. So, telescopes with large objectives provide high resolution and high magnification. It is important to note that the resolving power and the magnifying power refer to different entities. For example, if a double star system is observed by an astronomical telescope with a low resolving power as well as with a low magnifying power, the final image is as shown. It is neither well resolved nor well magnified. If we use an astronomical telescope with a low resolving power but with a high magnifying power, the final image of the double star system is as shown. We observe that the image is well magnified but not well resolved. If we use an astronomical telescope with a low magnifying power but with a high resolving power, the final image of the double star system is as shown. We observe that the image is well resolved but not well magnified. if we use an astronomical telescope with a high magnifying power as well as with a high resolving power. The final image of the double star system is as shown. We observe that the image is well magnified and well resolved. The telescopes we discussed so far are refracting telescopes, which use a combination of lenses. The big lenses used in telescopes of high resolving power are heavy. Therefore, it is difficult to make and support them by the edges. It is also expensive to make large-sized refracting telescopes that are free from any kind of optical defects. For these reasons, modern telescopes are reflecting telescopes which use a concave mirror as an objective. The reflecting telescopes use an objective mirror at one end of an open tube, which reflects light back to a smaller diagonal plane mirror to bring the collected light to the eyepiece positioned at the side of the tube. Some of the advantages of reflecting telescopes are: as there is no chromatic aberration for mirrors, it is completely eliminated in reflecting telescopes. Spherical aberration can also be removed by using a parabolic objective mirror. Since a mirror weighs much less than a lens, reflecting telescopes are easy to handle mechanically. In some of the reflecting telescopes, a convex secondary mirror is used to focus the incident light onto the eyepiece. When a narrow beam of white light is incident on a prism made of transparent material, it is experimentally observed that the emergent light consists of several colors. These different colors are continuous with no sharp boundaries between them. But we can still identify 7 prominent colors in that band of colors. Another important observation is that the colors always appear in a specific sequence. This sequence of colors is violet, indigo, blue, green, yellow, orange, and red. The sequence of colors can be remembered by the acronym VIBGYOR, formed by the first letters of all the 7 colors. It was Isaac Newton who proved that these colors are already present in white light, and that the prism splits the white light into its constituent colors. In order to prove this, a similar prism was inverted and placed in the path of the emergent light rays. It was observed that different colors emerging from the first prism, on passing through the second prism, combine to form a beam of white light. Hence, it was concluded that the prism splits the white light into its component colors. The phenomenon of splitting of white light into its component colors is known as dispersion of light. The band of color components of light formed by splitting of white light is called the spectrum of light. This spectrum of colors is also known as the visible spectrum, which is a small part of the electromagnetic spectrum. Now, let us further understand the phenomenon of dispersion. We know that the color of light is related to its wavelength. If the wavelength of light is in the range of 395 to 450 nanometer, then the color of the light is violet to indigo. If the range is between 450 to 490 nanometer, the color is blue. If the range is between 490 to 560 nanometer, the color is green. If the range is between 560 to 590 nanometer, the color is yellow. If the range is between 590 to 635 nanometer, the color is orange. If the range is between 635 to 700 nanometer, the color is red. Of the 7 colors, the red color light has the longest wavelength, whereas the violet color light has the shortest wavelength. Light rays with different wavelengths travel with the same speed in vacuum or air. When all these 7 colors reach the human eye at the same time, we get the impression of white light. But in a material medium, the speed of light is different for different wavelengths. More the wavelength of a light ray, more is its speed in any given transparent material medium. That means, in a medium other than air or vacuum, the speed of red color light is the highest and the speed of violet color light is lowest. This makes the refractive index of a transparent medium different for different colors of light. A medium in which the refractive index varies with the wavelength is known as dispersive medium. Hence, light of different colors bend through different angles while passing through a dispersive medium. Normally, we don't observe the effects of dispersion when light travels through a parallel-sided glass slab. A beam of white light that enters a glass slab emerges as a white light only. But, in fact, the white light splits into its constituent colors at the first refracting surface of the glass slab. And these component colors combine to form a ray of white light while emerging out of the glass slab from the second surface without any dispersion. We can observe the effects of dispersion of light in the case of a lens, especially if the lens is thick. For example, if a beam of white light parallel to the principal axis is incident on a thick convex lens, it gets dispersed at both the edges of the lens. As a result, rays of different colors are focused at different points on the principal axis. Hence, the focal length of the lens is different for different colors. The red rays have a maximum focal length, whereas violet rays have minimum focal length. This inability of the lens to focus all the colors at one point is called chromatic aberration. Because of this, multiple colored images of an object are formed at different focal points. The image formed by violet rays is closer to the lens than the image formed by red rays. In the case of a convex lens, these images are in the direction of the incident light and hence the chromatic aberration is positive. For a concave lens, the images formed are in the direction opposite to the incident light and hence the chromatic aberration is negative. It is possible that a suitable combination of convex and concave lenses may be free of chromatic aberration. Such a combination of lenses used to decrease the chromatic aberration is called an achromatic doublet. Usually the two lenses used in the achromatic doublet are made of different materials, like crown glass and flint glass.